Okay, so our next speaker will be Professor Samir Assuena, from Centro Universitário da FEI, também do INUSP. He will talk about constant cyclic codes as ideals in twisted group algebras. Samir.
Thank you, Cicero, and thank you, the organizers, for the opportunity to speak here. This is a joint work with André Duarte, who spoke the day before yesterday about idempotence in twisted group algebras. So I'm going to present the second part of our work, our paper, that deals with constant cyclic codes as ideals in twisted group algebras, and we study some, we try to classify some isometries between constant cyclic codes. Okay, so what is a constant cyclic code? It's just a linear code that is Sarah already has already defined. A linear code is just a FQ subspace of FQN, and if we take a non-zero element of this of the finite field of the field, we say the code is a lambda constant cyclic if we take any word of the code and apply the shift, and in the first coordinate multiplied by lambda, this word has to be in the code for all words in the code C. This is a lambda constant cyclic code. When we consider lambda equals 1, we have cyclic codes, and we have when we consider lambda equal -1, we obtain negacyclic codes. In that way, constant cyclic codes are nice generalizations of cyclic codes and negacyclic codes. Also, we know it's a very well-known fact. Constant cyclic can be realized as ideals in factor ring and factor polynomial ring FQX by the ideal generated by xn minus lambda. So our first result is to show the constant cyclic codes can be also realized as ideal in some twisted group algebra. We know it's a very well-known fact. When we study or when we work with cyclic codes can be realized as ideals in group rings. Okay, now we are going to show the lambda constant cyclic codes can be also realized as ideals in twisted group algebras. So since I'm going to talk about isometries, we need to define the Hamming distance between two elements. Is exactly the number of coordinates that two elements or two code words differ, and we define the weight of an word, just the distance between this element x to 0. It's well known for linear codes. The minimum distance is equal to the minimum weight of linear codes. Isometries between constant cyclic codes are mappings that preserves the Hamming distance. Okay. And what is a twisted group algebra? We start with a commutative ring. The ring needs to be exactly commutative, but we start with a ring R and a group G, and we define the associative algebra with basis G bar, and G bar is just a copy of the group G, and the multiplication is defined on the basis by G bar plus H bar is just an element gamma of G, applying G H plus G H bar, where this element gamma is a unit in the ring. Okay, it's element of the group of units of R. This mapping gamma, it's called twisting, and there are many different possibilities for the twisted group algebra, depending on exactly the choice of the twisting. For example, the group ring, the ordinary group ring, is can be considered as a twisted group algebra, just taking gamma equals 1. Furthermore, the associative condition on this algebra implies that this mapping satisfies this equation or this relation, and for this reason, this mapping gamma is a 2 cocycle, as André told us in his talk. We need to gamma, this twisting needs to be a 2 cocycle. Okay. So sometimes in this algebra we can make a diagonal change of base. We can just replace this basis G bar by another elements that are obtained from G bar, just multiplying this G bar by a unit in the ring R. And when this happens, we have another 2 cocycle, but when we look at the structure of the algebra with these 2 cocycle, they have the same structure. So when you make some diagonal changes or bases, the twisted group algebras have the same structure. In this case, we say that gamma tilde gamma tilde and gamma are cohomologous. So cohomologous 2 cocycle give us the same twisted group algebra. So we want to find or study twisted group algebras unless cohomologous, 2 cocycles that are not cohomologous. Okay. So our third result is just the following. Let FQ be a finite field, and if you take a cyclic group of order n and a linear code over FQN, and we can define just this mapping, and of course depends on the twisting, but defining the twisting just like that is just gamma if J plus R is greater than N, and 1 if J plus K is less N. N is the order of the group. We have the following situation. C is a lambda constant cyclic code if and only if the image of the code by this mapping is an ideal in the twisted group algebra FQ gamma Cn. Okay, so in this case, we can see the lambda constant cyclic codes can be also realized as ideals inside the twisted group algebras. Okay, this is our first result. And now we start to we try to classify or try to find some relations between isometries between constant cyclic codes. And our first result that we proved using just twisted group algebra structures, but we find out that Ginosar and Moreno proved this same result, but using this generalization of twisted group algebra, cross product of algebras. But the result is the following: that exists an isometry, that is a mapping that preserves Hamming distance between these twisted group algebras, if and only if gamma 1 and gamma 2 are cohomologous. Okay, in fact, this isometry is also an algebra isomorphism. Okay, so if you have two cocycles that are cohomologous, the twisted group algebra are isometries. The codings inside these two different group algebras are isometrics. Using this result, we can now classify or study when exists there some isometry between two twisted group algebra with these two cocycles for lambda and beta different. So there exists an isometry between these two twisted group algebra, if and only if the elements, the non-zero elements, lambda and beta, are related in that equation. So lambda has to be equals and some unit, some non-zero element of the finite fields to the n plus beta. And notice that the n here is just the order of the group, the cyclic group. Okay. So it should be mentioned that for cyclic groups and finite fields, or not just finite fields, but fields in general, they're the only class of cocycles are just defined by this cocycle and this equality here. Okay. So when the elements lambda and beta are related in this equation, these twisted group algebras are isomorphics, and there is this isomorphism preserves Hamming distance. Okay, and we have a corollary. Right? If we consider the ordinary group algebras, and the corollary is the following: there exists an isometry between twisted group algebra with the gamma lambda to cocycle and the group algebra FQCN, if and only if lambda is equals a for some non-zero elements of the field FQ to the n. Okay, it's just replacing in this proposition beta by 1, because group algebra are considered as twisted group algebras. Okay, we just replace beta by 1, and we have this corollary. And maybe the last result: if we take n a positive integer such that it's coprime to q minus 1, fq be a finite field, and cn cyclic group of order n. In this case, always exists an isometry between the twisted group algebra and the group algebra FQCM. Okay. Again, this isometry is an algebra isomorphism, and this result tell us that in this case the twisted group algebra is always isomorphic to the group algebra, and this isomorphism preserves Hamming distance. Okay. Just a remark, these results we proved in a more general case. Okay. These results we proved for replacing the finite field for finite, replacing the finite field by finite commutative rings. Okay. And thank you for your attention.